Hello medical students. In this video we will continue chapter 2 of our MCAT prep course. And these sections we're doing 2.4, 2.5, and 2.6 involve a fair number of formulas. So hopefully we can work through these, navigate this without too much trouble. The first section here, 2.4, is pretty short and it talks about something qualitative, open, closed, and isolated systems. So I'm going to talk a little bit about systems. So the idea here is that your system is just whatever you're interested in. It's whatever you want to analyze the behavior of. And so usually the problem will give you a good idea of what you should choose to call your system. So an open system, this means that both mass and energy can flow in and out. A good example, of course, would be a living organism like a human being. So I'll say you. You're an open system. Your weight changes over time. You can expend energy. You can have energy applied to you. You know, for example, when you eat and your body metabolizes energy, that's increasing energy, or when the sun shines on you, it heats you up, that's adding energy. And you can also lose energy and mass. So that's an example of an open system. A closed system, as the book defines it, it can't exchange mass. So it doesn't exchange mass, but it may exchange energy with its environment. Now, oftentimes you hear people say closed system and they'll mean that it doesn't exchange anything with its environment. So you should, oftentimes there's only two, open versus closed, and isolated is kind of a synonym for closed in that sense. So you have to be sure what a person means, or what a question means, or what a book you're reading means by it. These are not universally described this way. But an example of something like this would be, like for instance, if you have, what do you call those things? If you, like you put in your lunchbox one of those little cubes that has some kind of refrigerant in it, like, you know, an ice pack or something like that. So let's say ice pack, and stipulate that the ice doesn't melt and the water doesn't run out. It's just exchanging heat. So the idea is that you have here, you have the ice, and then you have here whatever the food is next to it, and heat energy can flow from the food into the ice, and that keeps it cold or whatever. So that would be an idea, but you know, the food doesn't physically move. The substance of it doesn't move here, nor does the ice move into there, nor does water flow across or anything. It's just heat energy that's being transferred in that case. So this is a case of what the book means by closed system. And then isolated. An isolated system would mean no mass or energy transfer at all. And the book uses the universe as an example of this, and it's not a good example because, so I'll put 3 question marks here for that it's kind of a suspect example because when you talk about the universe as a whole, it opens cans of worms. I mean, for instance, space-time appears to be expanding, and there's this thing called dark energy, which appears to be a attribute of space-time itself. So the more space-time you get, the more dark energy you get. And so it looks like on a cosmological level, you're getting energy for free in that case. And so that's not a good example. But you could have, you could say a better example would be something like a planet. Say you had an icy planet far out in space, not close to any stars or anything. So let's say planet far out in space. Now, a planet like Earth would not be a good example because, of course, it's getting lots of energy from the sun. But if you had a planet that was way far out away from any stars, then it would be a reasonable approximation of a closed system. Of course, if it had some temperature, it would still be radiating energy into space somewhat. But, I mean, I could say, like say I have a black hole far out, so this would be black hole. Even a black hole will radiate somewhat. That's called Hawking radiation, but it's a very good approximation of something that neither receives energy or mass, nor does it expend energy or mass. So these are kind of the ideas. But to summarize, just think about it on a more simple level. Open, it can interchange anything, mass, energy. Closed, it doesn't physically, it mechanically exchange anything like different pieces or whatever, but energy can flow back and forth, and then isolated, nothing flows back and forth. Okay, so let's go to the topic of energy now, more specifically. So, energy. Now, the book tells you, and this is a good way to think about this, most of the problems you're going to encounter that involve energy, you're thinking about a ledger or balancing a checkbook or something like this. This is why it says accounting. See, usually it's going to involve some idea of energy conservation, some kind of conservation idea. And so this is, I guess I could even put this in parentheses up here. Now, it's not always going to be conservation, but that's usually what's involved in this context, where this idea of accounting, you're thinking about how much energy leaves. Well, the same amount of energy has to flow in if the total energy remains the same. Or saying, all right, well, if I have a total amount of mechanical energy and it starts out as potential energy, then some of it's converted to kinetic energy. I can find out how fast an object's going by figuring out what the change in potential energy was and assuming this gets converted to kinetic energy. That's this last equation down here that I wrote. So the first thing, though, is units. And by this time, we've been dealing with units enough to where it's worthwhile to take a second to just go through the level of complication that we've gotten to. So this equation here, this is kind of a good way to remember what the units are. So this is a particular equation that tells you a particular type of work in a mechanical setting, which is work. What this is saying here is work equals force times distance. And later you'll get a cosine theta in there, and that's when you're not pushing directly in the direction that the object is moving. So the force is, this is force applied to an object. The distance is the distance the object moves as a result of the force. But you can use this particular equation to help you figure out what the units are. So force, you remember force, you have this F equals ma. This was Newton's second law. And so what this is saying is that force is equal to mass times acceleration. Well, mass, we've broken that down all the way. That's kilograms. Acceleration, that's a little bit more complicated, but you know what it is. It's meters per second squared. So here you've got kilogram meters per second squared. And then that's the force. So all of this, and this, by the way, of course, is a Newton. It's abbreviated to Newton. But all this is the force. And then you've got another distance, which is in meters. So what this all boils down to is that the work is going to be in kilogram meters squared per second squared. And that's what's called a joule. So this was named after a French guy, I guess, but it's convenient not to capitalize it. So it's just an abbreviation. It's a word. You just think this is a word that means this. And the unit is written J like this, just like Newton is written N. So whenever you're asked for work or energy, it's always in joules, and this is what the joules mean in this context. Okay, so now we begin to discuss a bunch of different types of energy. So I'm going to doctor this up here a little bit. So this will be types. So this first one here, I guess I can say I've done that, I've done that, I've done that, I've done that. This first one here, kinetic energy. This is kinetic energy of a moving mass. And so the idea is you have a mass, and that the mass is m, measured in kilograms. It's moving at a velocity of v, and the energy is, I guess I called it K there for kinetic, so I'll continue that. Kinetic energy, so K for kinetic equals 1/2 mv squared. This can tell you counterintuitive things about certain mechanical events that can happen. For instance, if you say you get in a car accident at 50 miles per hour, well, so that's your velocity there, v. And then if you compare that to getting in a car accident at 70 miles per hour, well, if I squared this, so if I square this will come out to 2500 if I square the 50. If I square the 70, it will come out to 4900, which is nearly twice. So this is telling you the destructive energy that's available to mess you up in your car if you hit something at 70 is twice as much as it is at 50. So in a sense, it's twice as bad, even though it's not even 50% again as fast. From 50 up to 70, it's twice as bad to have an accident at that speed. If you go up to 100, then this, if you square it, you get 10,000. And so that's more than twice as bad as this. So, getting in an accident at 50 miles an hour is bad enough. 70 is twice as bad. 100 is 4 times as bad. So, don't speed. That's kind of the moral of that little thing, I guess. All right, so let's talk about potential energy. Guess I'll clear this off. So there's lots of different kinds of potential energy, and before I forget, I'll mention the point of this note over here. See, in elementary physics, a lot of the ways in which you encounter energy is in a mechanical way. Either you'll have some object moving, or you'll have some object that's at a certain height, and so you say it has gravitational potential energy or something like that. But in medical settings, it's often the case that energy and energy transfer are things that are important at the molecular level. And so even though it's the same general concept, it's encountered in a microscopic way, a much smaller way, rather than these macroscopic sort of mechanical settings. And an example that's mentioned in the book is the conversion of ATP, adenosine triphosphate, to ADP, adenosine diphosphate, which powers molecular machinery. So here you've got potential energy stored in chemical bonds. There are 3 phosphate groups, and they have, and this actually comes down to its electromagnetic potential energy. It's the electrons are in a certain configuration that stores energy, and then when it donates one of these groups, the energy level drops, and that energy is converted into work for the cell or for the cellular machinery in that context. So that's an example that is an important example at the metabolic level. But we're going to see most of our examples in mechanical settings. So potential energy, there's one important type, and there's many different types of potential energy, but one type is gravitational. And so the idea here is you have a height. So you say you have a cliff here, and say you have a mass up at the top of the cliff. Well, provided that we agree to call this height 0, then the gravitational potential energy, we call this UG here, is going to be m times g times h. Now notice that mg was a force. That would be the force due to gravity on this. So this is kind of like a force times distance thing. So you can see that the units of this are correct. That's one way. Now, it actually turns out, and the book explains this, it turns out that you should really think of gravitational potential energy as something that's due to the gravitational attraction of 2 different bodies. But because we're often thinking about a very small mass compared to the Earth, and then the gravitational attraction of the Earth, it makes sense to think about just from the point of view of this particular mass, and we can use this approximation, and that's all that we need to say about that. Now, another kind of potential energy is, and this, by the way, I've written potential here, and then I've gone on to elastic, but this elastic is a type of potential energy. So this is elastic or spring potential energy. And the way this looks is you have a spring, and so I'm going to draw a spring, and I'm going to say the spring would be like this if it's not stretched. And then if I stretch it out, it's going to go like this. And you remember seeing pictures like this before where I called this delta x. I don't know why I'm putting a K. I'm thinking ahead of myself here. Delta x. In both cases, the spring constant here is K. And so it will turn out that the elastic energy or the spring potential energy in this system is going to be 1/2 times the spring constant times the square of this amount that the spring is deformed. Now, this whole thing, it's the whole delta x, it's the change. This is a single thing here. It's the whole delta x that's squared. It's not delta and then x squared, but it would be, I mean, if I wanted to, I could write it as 1/2 k delta x squared, just to be clear about that, but that would be messier. So I'm going to go ahead and continue to write it like this. Now, in a mechanical situation where you don't have transfer of heat or essentially microscopic forms of energy, mechanical essentially means macroscopic, large scale, mechanical, you know, large things moving or having energy because it's compressed or because it's a certain height in the gravitational field or something like that. That's the context of what mechanical means. So the total mechanical energy is going to be just the sum of these two. So total mechanical energy. Now you can have lots of different types of kinetic or potential energy involved in this. So the total potential energy, and I'm messing up my board here, but the total potential energy here would be U. And then there's different kinds. There's the gravitational potential energy, there's elastic potential energy. You could have electrostatic, you could have energy from an electric field or something like that. But the total mechanical energy is the kinetic energy plus the potential energy, and this is generally broken into several different parts. I mean, for instance, you could have, if you have a, say you have a mass hanging from a spring, like this, and it's going up and down, it's oscillating up and down. Well, whenever it's at a certain height, it has a certain gravitational potential energy, but the spring is also compressed a certain amount, so it will have a certain spring or elastic potential energy, and then it has a kinetic energy, which is determined by how fast it's moving. So in this potential energy part, you can have multiple contributions from different kinds of potential energy. Okay, so I've got this, this, and this. And we can clear this off now.